Okay, hi everyone. Today we're going to go through the solution for carboxylic acid and its derivatives. All right, okay, let's look at the first question. All right, this is compound T. So compound T is warm with aqueous sodium hydroxide, and then the resulting solution is cooled, acidified with dilute nitric acid, and then you add silver nitrate to the product, right? So this is actually testing for the presence of chloride because silver plus will react with Cl minus to form silver chloride. So you'll see which one will give you the PPT, right? So this actually is a hydrolysis question. So generally you need to know a few things, right? Acyl chloride will react with just water, all right? Just with water at room temperature, you get RCOH and HCl, right? And this HCl will dissolve in water, you form Cl minus aqueous ions, right? Okay, let's look at the next one. If I give you a normal alkyl halide, something like this, right? This one will actually have to react with sodium hydroxide, okay? And then with that, nucleophilic substitution can take place. You can break this CCl bond. So this is only for alkyl halide, this alkyl halide. Right? Okay, so generally you get R, CH2, CH2OH, and then you get Na plus and Cl minus. So the Cl minus is being kicked out, right? Okay, the other two that cannot undergo base hydrolysis will be this one, aryl halide, the Cl attached directly to benzene ring, because there will be partial double bond character where the lone pair can delocalize into the benzene ring. So the CCl bond is being strengthened. Okay, the other one that cannot undergo hydrolysis will also be when the Cl is attached to a carbon with a double bond, right? When the Cl is attached to a carbon with a double bond, it's the same concept, all right? So the lone pair can delocalize into the CC pi bond, right? CC pi bond over here. So these two will not undergo base hydrolysis, which means if you add for these two, right, if you add sodium hydroxide and heat, actually theoretically the Cl doesn't get removed, right? The CCl bond doesn't get broken. So based on this question, so which CCl bond can be broken? There are only two over here, the alkyl halide and this acyl chloride. Okay, these two can kick out the Cl minus, right? Can kick out the Cl minus. All right, this one, the Cl is attached to carbon with a CC double bond, no reaction. This one, the Cl is attached to benzene ring, also no reaction. So that's definitely the answer is just 2, right? Okay, let's move on to the next question. Okay, consider for carboxylic acid, which is the relative order of decreasing pKa. So actually means what they're trying to say is from high pKa, right, high pKa to low pKa, all right? So which means this is high means a weak acid, weak acid to stronger acid, yeah, all right? So which is the strongest acid? Okay, the strongest acid is probably the one that can form a stable conjugate base, right? So actually if you look at it carefully, it's this one that can form a stable conjugate base. It's actually number 4, right? Why is that? So when we look at pKa, we're actually looking at the Ka of these acids. We're looking at all these. So I'm going to draw out very quickly, all right? So let's look at the conjugate base of this carboxylic acid. So when you form the conjugate base over here, all right, let me just draw nicely. Okay, when you form the conjugate base over here, this is a quite stable conjugate base because there is actually hydrogen bond. Can you see that? There's actually hydrogen bond. So this hydrogen bond stabilizes this CO minus, right? So which means the strongest acid must be number 4. Okay, I'm just going to put 4 here first. Okay, let's look at the next stronger acid. Okay, you need to know that electron donating group will actually make it a weaker acid, and weaker acid if it's an electron donating group. Okay, so over here there are 2 electron donating group, but which one is a stronger electron donating group? Is actually OH. So the lone pair of O can delocalize in the ring. Okay, but CH3 is just electron donating. It's just mildly electron donating. So let me draw it out very quickly. So let's look at this compound. Let's look at number 3. All right. So this negative charge, actually this negative charge is supposed to be able to delocalize into the benzene ring. Okay. All right. It can delocalize in the benzene ring. So actually this is how it works. Okay, the negative charge can delocalize to this carbon and actually into this oxygen. At the same time, it can delocalize into the benzene ring. So if OH is electron donating, all right, it increases the electron density in the benzene ring, all right. So the negative charge, less of the negative charge can delocalize into the benzene ring, less of it, because of the high electron density in the benzene ring. So less can delocalize. So this negative charge is dispersed to a lesser extent. Okay, so if it's dispersed to a lesser extent, all right, it means it's actually going to be the acid is going to be a weaker acid. Okay, it's going to be a weaker acid. So the weakest acid here is actually number 3. Okay, then the next weaker acid is CH3. CH3 is also electron donating, but it's only mildly electron donating, unlike phenol. All right, so it's mildly electron donating. It also make it a weak acid, but it's not as weak as with OH group attached to the benzene ring. So the next weaker acid is number 2. All right, and then 1, because 1 has the absence of any, there's the absence of any electron donating group. All right, so it is actually stronger than 2 and 3. All right, stronger than 2 and 3. So the answer for this question is actually 1. All right. Okay, let's look at the next question. Okay, which of following will not react with cortisol? All right, so let's write all the functional group. Okay, you have a ketone over here. Okay, you have an alkene, you have a secondary alcohol, you have a ketone, you have a primary alcohol, and you have a tertiary alcohol. Okay, so these are all the functional groups. So sodium carbonate, which of all will not? Okay, sodium carbonate will only react with carboxylic acid. So which means since it doesn't have any carboxylic acid, so sodium carbonate has nothing to react with. So that's why A is the answer. A will not react with cortisol because cortisol doesn't have a carboxylic acid group. Okay, red phosphorus and excess Br2, basically this forms PBr3. And PBr3 can actually react with alcohols and carboxylic acid, right? Okay, so the alcohols, all the OH will be replaced with a Br. Okay, all the OH will be replaced with Br, which means it can take place. Co-alkyl KM4 will react with alkene, okay, to form diol. All right, to form means so there's an alkene over here. Yes, it can react. 2,4-DNPH is of course to react with carbonyl. Right, so there's a carbonyl here and carbonyl here. So that's why the answer is A. Okay, let's look at the next question. All right, let's look at the next question. Okay, compound P has an unbranched carbon chain and aqueous solution of P has an approximate pH of 3. So which means it's probably acidic, right? Q is a secondary alcohol. So they react together with concentrated sulfuric acid, and then I think you form a major product, and this major product is your ester. Okay, so you probably get an ester over here. All right, so firstly, P must, since the pH 3, P must be a carboxylic acid. All right, and then it will react with the alcohol to form the ester. So since this is an unbranched chain and there are 4 carbons, so I'm going to just draw it out like that. 1, 2, 3, 4. All right, so this is probably P. Okay, this is actually P. Okay, P will react with a secondary alcohol. Okay, this is a secondary alcohol and there are only 3 carbon. So I'm going to draw a secondary alcohol over here. So secondary alcohol means it must have 2 R groups. And there are only 3 carbon, right? So this is the only way I can draw it. Okay, this is a secondary alcohol. So what you need to do is to form an ester, you take away OH from here and a H from here. So this is what it should look like. CH3, CH2, CH2, COO, CH, CH3 and 2 of it. Okay, so which means B is the answer. All right, so that I have that structure here. All right, so that's how we do it. Okay, let's look at question 5. When halogen S, compound S was brought under reflux for some time, with silver nitrate, a mixture of ethanol and water, little or no PPT was seen. Which of the following could represent S? Alright, so when you react with silver nitrate and a mixture of ethanol and water, essentially the water or the ethanol will act as a nucleophile to kick out the carbon, right? To kick out the halogen. So generally this is what happens, right? If you have a carbon here, right? So just an example, say so this delta minus, this delta plus, right? So you will have, say, water or ethanol, it will act as a nucleophile. It will take the carbon to kick out the Cl, alright? So they say there's no little or no precipitate was seen. So in this case, I'm thinking which halogenal compound will not react with a nucleophile like this. It must be a aryl halide, okay, aryl halide, because it has partial double bond character. So definitely the answer is D, right? So this one again, we just went through just now. The lone pair of Cl can delocalize into the benzene ring, so causing the CCl bond to have partial double bond character, or partial double bond character, yes, and the CCl bond is strengthened. So this one will have no reaction. Okay, so you cannot kick out the Cl even in a mixture of ethanol and water and you heat and you boil it. Yeah. Okay, let's look at question 6. Okay, how many isomers of this molecule will liberate hydrogen gas on reaction with sodium? Okay, so which means this molecule should be an alcohol, alright? So they want to include structural isomers and stereoisomers, which means you also have to consider like your cis trans or even your chiral center, your enantiomers. Okay, so let me try to draw the first one. Okay, I'm not going to draw the hydrogen, but you should know the hydrogen are there. So there are 4 carbon, alright? I'm going to draw OH here. So this is the primary alcohol, alright? So I can say this is a straight chain because all the carbon is a straight chain. I can also draw this straight chain carbon, alright? But I put OH on the second carbon. So this is another possible structure. So 2 already. Okay, but the only tricky thing I want to say about this one is, you notice I put a H here, this carbon becomes a chiral center, alright, which means this one has 2 and this one has 1. Alright, okay, the next one I'm going to draw, alright, the next one I'm going to draw would be branch carbon chain. So 1, 2, 3 and the 4th. Okay, so if you draw this compound, you notice you can put the OH on any of this carbon, this one, or this one. They put OH on any of these carbon and it will still be the same compound. Alright, so I'm just going to put in the OH over here. Alright, so this is another one. There's no chiral center in this structure, so another one, I put 1. So the next one I can also draw is the same thing, a branch hydrocarbon, but I'm going to put the OH over here. Right, which means and this one doesn't have any chiral carbon, so 1 or so. So work it out. So 1, 2, 3, 4, 5. So this answer would be D. Alright, so that's how it's done. Okay, let's look at next question. Which transformation will involve a nucleophile? Okay, which involve a nucleophile. Alright, so if you look at this this reaction, right, this NHNH2, it looks a bit like 2,4-DNPH, right? It looks like 2,4-DNPH. So in fact, how does the 2,4-DNPH work with carbonyl? It acts as a nucleophile. So I'm just going to show you the very first step of how it works. Alright, just give you a rough idea how it works. Okay, so you have a carbonyl here, alright, CH3 over here. So this is delta minus, this is delta plus, right? So I'm going to just draw this out quickly. NH. So this is like a 2,4-DNPH, of course. So the lone pair of N here acts as a nucleophile to attack this carbon. Can you see that? The electrons go to the O. So eventually you still get this compound, but you can see that it acts as a nucleophile because of the lone pair on N. Alright. Okay, this one, if you number 2, I think this one you're more familiar with it. Cn minus, okay, acts as a nucleophile, delta minus, delta plus, okay, O more electronegative of course, and the lone pair attack this carbon. Electrons go to the O, so that's roughly the mechanism. Okay, so 1 and 2 are correct. And last one, the nucleophile. What's the nucleophile? If I try to draw the acyl chloride, okay, this is the acyl chloride, and then if ammonia, this ammonia, so the lone pair N again acts as a nucleophile. Alright, so generally it's this delta minus, and this is very delta plus, and actually the N will attack this carbon. So the ammonia acts as a nucleophile again. So the answer has to be D. Okay, let's look at next question. Number 8. Okay, which organic compounds, when added separately to water, solutions of increasing pH values are obtained. So increasing pH values means it's from like acidic to basic. Okay, so these two are actually amines, right? These two here are actually amines, and amines are actually basic. All right, they have a lone pair on the end, right, to accept the proton. So these two are acidic. All right, but this is only acidic in water. If you put it aqueous, it'll be acidic. So anyway, they're added to water. So this is highly acidic, as you can remember. Okay, acyl chloride, just in water, it will produce CH3, COH plus HCl. Okay, so the HCl makes it very acidic. So I guess I will pick either C or D. All right. Okay, and then next will be this two. So we have to decide which is more basic. I'm going to draw the two amines. The first amine look like this. And the other amine look like this. Okay, so this amine here has 3 carbon. So we will take it as is more electron donating. It will increase the lone pair, the electron density on N to a greater extent, which means this guy should be more basic, right? Compared to this one, only has 2 carbon, so less electron donating. So the one that's more electron donating will increase the electron density of N to a greater extent, and it will have to be more basic. Okay, so which means the answer has to be D, because this is the most basic over here. All right, so the answer is D for number 8. Okay, let's look at the next question. Which statements about the formation of carboxylic acids are correct? Okay, let's try. Carboxylic acid can be produced by oxidation of a primary alcohol. This is correct. A carboxylic acid can be produced by reduction of nitrile. No, when you reduce a nitrile, okay, what happens when you reduce a nitrile? When you reduce a nitrile, in fact, you get an amine, RCH2 NH2. Okay, you get an amine. So this is wrong. Okay, carboxylic acid can be produced by reduction of aldehyde. No, actually an aldehyde is not reduced. An aldehyde is oxidized, and then it becomes a carboxylic acid. Yeah, must be oxidized. So this one is definitely wrong. Okay, so carboxylic acid can be produced by hydrolysis of acyl chloride. This is right, because just now I've been doing this one. Acyl chloride undergo hydrolysis means just in water. Okay, just in water, it will produce RCOOH plus HCl. Okay, plus HCl. Alright, so you get a carboxylic acid over here. Okay, so this is correct. So answer has to be 1 and 4. Okay, 1 and 4. Okay, let's look at the next question. Okay, what's the maximum number of bromine atoms that can be incorporated when gaseous HBr reacts with chlorogenic acid? Okay, HBr gas. Okay, HBr gas, right? HBr gas actually only reacts with two things here. I'm going to just tell you. It will react with alkene. And it will react with alcohol. Okay, I said alcohol. So the OH will be replaced with a Br. Okay, the OH will be replaced with Br. If it's alkene, then of course you understand that it undergoes electrophilic addition. Okay, electrophilic addition. Okay, so I'm going to just circle with the ones that can be replaced. So this alcohol, okay, OH replaced with Br. 1, 2, 3, right? It doesn't react with carboxylic acid, so this one there's no reaction. It only reacts with alcohol. So another thing it can react with is the alkene. So I can actually put a Br here, and I can also put a H here, right? Yeah. Okay, so very quickly, how many Br did I replace? 1, 2, 3, 4. Okay, 1, 2, 3, 4. So the answer is B. Okay, the answer is B. Okay, let's look at the next question. Okay, 11. Okay, the diagram shows the structure of L. L reacts with lithium aluminum hydride and dry ether to give a cyclic compound M. Okay, let me just draw what's M. Then hopefully everything will make sense. So lithium aluminum hydride will reduce ketone, and actually it will reduce this ketone, and I'm just going to say this, it will convert an amide to an amine. Alright, so I have to go and draw it up for you. It doesn't react with alkene, so the double bond here remains the same. Okay, just let me draw this out quickly. Okay, this is alcohol, CH3 over here. So this one becomes NH. Okay, the C double bond O, this one becomes CH2, and this one this remains CH3. This is my alcohol. Okay, this is the CH3. Alright, okay, this part is a bit tricky. If you look at it carefully, you realize it's CH2. Okay, notice it's CH, which means actually there is a double bond here. Right, that was a bit tricky. Alright, so it reacts with ethanol acid to form 1 mole of amide. No, amide is only formed from acyl chloride and amine. It reacts with 2 moles of 2,4-DMPH. I don't see any carbonyl, so yep, it's wrong. It reacts with sodium metal to produce 1 mole of hydrogen. So where would it react with? It will react the OH from here and the OH from here. Alright, so when it reacts with this 2 OH and this H and H comes out, it forms H2. Okay, so it forms 1 mole of hydrogen, correct? Okay, it reacts with acidified potassium manganate to form 2 moles of carbon dioxide. The truth is this: if you actually if you oxidize this, break this 2 double bond, and you break this double bond, in fact, this carbon will become CO2, this carbon becomes CO2, and this carbon also becomes CO2. So which means actually you don't get 2 moles of carbon dioxide, you get 3 moles of carbon dioxide. So this statement is actually wrong. Okay, so the answer is going to be C. Alright, okay, let's move on. Next question. Question 12. The following compound is heated with water for a prolonged duration. So prolonged duration, what happens is this. Okay, maybe I'll just say this. Just with water, this Cl will become OH. This goes to acyl chloride. Okay, this acyl chloride, acyl chloride. So it can undergo hydrolysis very easily. Okay, it can undergo hydrolysis very easily. Okay, so how about this one? This one, you notice this Cl is attached to a carbon with a double bond. So this one has partial double bond character. This one, no reaction. I'm going to put out no reaction. Okay, this one is partial double bond character. There's no reaction. How about this 2Cl? Okay, because of the prolonged duration, the water can act as nucleophile and is able to kick out this 2Cl. So what happens is this. I'm just going to draw it out. So in fact, the 2Cl become OH and OH. And if you remember, this is called germinal diol. Okay, which means it's 2 OH attached to the same carbon. So when that happens, it's very unstable. In fact, you must take away water. Okay, you must take away water. So water will be eliminated naturally. You don't have to do anything because it's very unstable. So in fact, the end product will be a ketone. Okay, the end product will be a ketone that looks like this. So which means this is going to be the answer. Okay, so that this will be the answer. Alright, so that's why it's going to be C. Okay, let's move on. Next question. Question 13. An organic compound is converted into a carboxylic acid using 1-step or 2-step synthesis. Which of the following cannot be Z? Okay, so which one is Z? It can be converted to a carboxylic acid. Alright, so for A, okay, A is a bit tricky. But if you realize A, alright, this is A, so there's a H over here. So this one can undergo iodoform test. Okay, iodoform test. So A, maybe just show you if it undergoes iodine, sodium hydroxide aqueous, and warm. Okay, this is your product in fact. Okay, this carbon will become C double bond O, O minus. Then if you further add H plus aqueous, okay, this one plus of course CHI3. Alright, if you continue to add H plus, of course you get your COOH. Okay, so you have 2 steps. Okay, let's try this one. Okay, this one I'm just going to say this. Over here you can add HCN, trace KCN. Right, so what happens? Your carbonyl becomes a cyanohydrin, and after that you can also add H plus and heat acid hydrolysis. So what happens? The CN becomes COOH. Can you see that? So you show 2 steps. Okay, how about B? Okay, B the same thing. In fact, I can add KCN in ethanol and heat. Alright, so this is what you get. So it becomes CN, and then of course again you add any strong acid and heat. Okay, so the CN becomes COOH. Alright, so the only answer that will not give you a carboxylic acid is actually D. Don't believe it, try it and see whether you can give me something that because even you use KMNO4 and you oxidize this, you get a ketone. Alright, you get a ketone actually. Alright, okay, let's move on. Question 14. Which of the following is true about vitamin A? White fumes is observed when treated with excess ethanol chloride. Okay, ethanol chloride is highly reactive, and every time you react with this, generally you get white fumes. Okay, so I'm just gonna draw it out over here. So over here, you notice if I draw the ethanol chloride, alright, you end up getting the ester. So I'm going to call this part the R group. Okay, I'm just going to keep it simple. So you take away HCl, so you get RO, C double bond O CH3, alright, and HCl. Okay, so this HCl will come out as actually white fume. So acyl chloride is always highly reactive. Usually when you react with it, you get white fumes, right? So definitely the answer is A. Right, answer is A. Right? Okay, let's move on to the next one. Phenol propanoate. So is how to draw phenol propanoate. So this one comes from the hydroxy compound, alright, which is phenol, and then this one comes from the acid, actually the propanoic acid kind of a site. Okay, so let's see how we draw it. Okay, this is what we are supposed to draw. Okay, phenol propanoate. So you have O, C double bond O, propanoate, right, means there are 3 carbon. 1, 2, 3. Right, so keep it simple. Present water labeled with deuterium. So this is water, okay, but it's not H, it's actually deuterium. So if you use it, if this was a nucleophile, delta minus, delta minus, delta plus, the lone pair will attack this carbon. Okay, the lone pair will attack this carbon. Sorry. Okay, the lone pair as a nucleophile attack this carbon, and this bond will break, and this will break. Okay, so eventually I'm just going to skip it really straight to it. So become O. So this D will actually go to the O. Okay, see that? So you get OD, and the other side will be C double bond O, CH2, CH3, and this OD will join to this carbon, so it's OD. Okay, alright, OD over here. So if you look at your answer key, look at answer key, I will probably get 1 and 2. Okay, I get 1 and 2, so answer is B over here. Okay, let's look at question 16. Excess sodium carbonate is mixed with phenol methanol. So phenol methanol is this one here, which is an alcohol. Of course, you can draw phenol. And last one is methanoic acid. Okay, let me just draw it out again. Methanoic acid is just HCOOH. Okay, so which of the organic species are present in the organic layer? So the organic layer is the one that didn't react with the sodium carbonate. So this one will actually react with sodium carbonate. You get COO minus, becomes AQ. All right, become AQ. Of course, you get carbon dioxide and water. Of course, all right, when you react with sodium carbonate. Okay, so this one, it will be in the aqueous medium, and all this will be in organic because I'll just take it as still in the liquid form. All right, so you get phenol, methanol, and phenol. Okay, good. Let's move on to the next question. So it's D. Okay, when a compound V is reacted with excess reducing agent followed by heating with excess concentrated sulfuric acid, it gives only one. See, they highlighted it, only one final product. So what could it be? All right, okay, let's run through. So hydrogen will reduce, okay, and this is the molecular formula. All right, this molecular formula. You notice there isn't any more O. Okay, this will reduce only ketone. There's a carboxylic acid and there's a ketone, but hydrogen only reduces ketone here. It doesn't reduce the carboxylic acid. So this is the thing I'm going to draw. All right, you get OH here. All right, okay, I'm going to draw all of them first. So this one here, sodium boron hydride will reduce both, will reduce this ketone to secondary alcohol. In fact, this is an aldehyde. You see, aldehyde will be reduced to a primary alcohol. Okay, this is a primary alcohol. Lithium aluminum hydride will reduce both, okay, ketone as well as carboxylic acid. So the carboxylic acid will become a primary alcohol. Okay, this part here, now when you add concentrated H2SO4, alright, so the mechanism we are looking at is actually elimination. Okay, you take away water. So what can you possibly get? Okay, what can you possibly get? So you realize that if I take away this OH from here, I can take away a H from here or H from here. So there are actually two possibilities, right? In fact, there are two possibilities. Your double bond could end up over, if you take away OH and a H from here, the double bond will be here. If you take away OH and a H from here, the double bond will be here. So you get two different products. But the questions only say only one final product. Okay, if you did this next one here, all right, with concentrated H2SO4. Okay, so I'm going to take away the H from here. Can you see that? So the idea is you're going to get a double bond over here. Okay, a double bond over here. Okay, there's a H here and there's a H here. So you could actually take away OH and a H from here. The double bond could be here. And of course, the other possibility, if you take away OH and a H from here, the double bond will be here. So again, you get two different compounds. Okay, this one here, I'm going to take away the H and OH. So I'm going to draw the first part. Okay, a double bond here. Okay, so over here, you notice I could take away the OH and the H from here, and I get a double bond. Or, what happens if I take away the OH and the H from here? The double bond is here. Alright, but if you look at it carefully, in fact, these two are the same. Can you see that? Okay, it's actually they're the same. You just have to flip it 180 degrees, you realize they're the same. Okay, which means this only gives you one product. Okay, it's actually one product, right? So definitely 3 is the only answer, D. Okay, so that's how we do it. Okay, let's look at question 18. They say acetic acid can be synthesized in 2 steps starting from R. So let me try to show you how I can go about doing it. Okay, R. Okay, let's see which is the possible answer. Okay, this one I'm just going to do with, if you remember, is concentrated H3PO4 industrial process, or you can use a laboratory process. You add steam. Steam means water. I put gas. Okay, steamer. Okay, high temperature and pressure. Okay, high temperature and pressure. So you're gonna add water across the double bond, right? So you can apply Marconi-Kaw's rule because this carbon has 2 H's and this one is 1 H. So you're gonna add water, you add a H to the carbon with more H's, right? So the first thing I'll do is I'll probably add a H to this carbon, this carbon I add H, and then the other side OH. So this is the intermediate. Okay, the next step you can do is you use MnO4 minus. Okay, acidify and heat. Okay, acidify and heat. Okay, so this primary alcohol on the left hand side becomes a carboxylic acid. Can you see that? Becomes carboxylic acid, and this part here becomes a ketone. This secondary alcohol becomes get oxidized to a ketone. So that's why you can get a product. Okay, the next one here I will probably use sodium hydroxide, aqueous and heat. So acyl chloride actually will in the water form carboxylic acid, but because it's a basic medium, I will draw it like that, O minus. And the Cl will by now be replaced with a OH. Okay, and if I add KMnO4 minus, acidified and heat, the acid will go to the O minus, so you end up getting a carboxylic acid and not the salt anymore. The secondary alcohol will be oxidized, so it will be oxidized to a ketone. Okay, so it'll be oxidized to a ketone. You also can get it. Okay, the next one, I'm just going to say this. I have 1, 2, 3 carbon, but you notice this one has 1, 2, 3, 4 carbon. So you need 1 more carbon. So this one is you add your KCN, ethanol, heat. Okay, so the Br becomes Cn. Is okay? And then the next step is just acid hydrolysis. Okay, acid hydrolysis. So the Cn becomes COOH. Okay? Okay, so the same thing. So actually you get the same compound. Alright, so this question means it's 1, 2 and 3. Okay, let's look at the next one. Last two. Okay, which of following shows the correct order of increasing order of acidity? So the one that is most acidic, I think we've done this enough, right? The one that's most acidic is actually Q, in the presence of water, because once you put in water, this guy in water, right, we did a few questions already, plus water, you form CH3. So in presence of water, you form CH3, CH2, COOH, as well as HCl. Okay, so if the HCl, you know that's going to be very acidic. So I'm going to pick these two, okay? Q is being the most acidic, all right? Okay, so actually we only have to consider R and S. So again, between Cl, okay, between Cl and Br, okay, between Cl and Br, so the one that's most acidic is the negative charge that dispersed to a greater extent. So Cl being more electronegative. Okay, being more electronegative. Okay, being more electronegative than Br, it will actually help to disperse the negative charge to a greater extent. So which means this is what I'm going to draw. All right, CH2. Sorry, yeah. Not sure why it's like that. Okay. Okay, so this C double bond O minus. All right. So this Cl here is more electronegative, so it can actually pull and disperse the negative charge to a greater extent. It means R will be the stronger acid. Okay, so R being the stronger acid, the answer must be B really. Okay, must be B. All right. Okay, so let's try the last question, question 20. Okay, with sodium hydroxide, I'm going to draw F first. With sodium hydroxide, okay, what will react? In fact, the Cn undergo acid hydrolysis. This one undergoes nucleophilic substitution. The ester will undergo base hydrolysis. The Br on the benzene ring, there's nothing is going to happen. So I'm just going to draw F first. Okay, I'm going to draw F. Right. So C becomes, over here, C becomes C double bond O minus. Okay, this one also becomes CO O minus. The Br becomes OH. This one is OH. Okay. Okay, this is my F. Okay, this is my F. Okay, so after that, when you add acid, okay, so I'm just gonna add acid, right? So acid, I'm just going to draw it out there on this compound. So how to get, when add acid, this one becomes COOH. This one also becomes COH. All right. So the last step, you're going to add PCl5. So when you add PCl5 will react with all the OH from carboxylic acid and alcohol, carboxylic acid alcohol. So the OH here be kicked out, the OH here be kicked out, and the OH here be kicked out, and the OH here will also be kicked out. So all of them will be replaced with a Cl. All right, all the OH that circle will be replaced with Cl, which means the answer can only be C. All right. Okay, so that's how we do the 20 questions. All right. So this, I hope these 20 questions will give you some idea of what to expect from your school MCQ when it comes to organic chem. Thank you for watching the Twig Learning Center chemistry tutorial. I hope you learned something new. Don't forget to click the subscribe button so you'll be updated when new videos are posted.